Video? Okay. This one?
I only saw 4 of you declare the
Which camera?
so I need that all of them. All the rest to be today.
It's fine now?
Huh? Oh, yeah.
Okay. Let's get started. Okay. So two quick recaps. So whatever we covered today, until this class is, we started talking about normal distribution, then we gone to Gibbs law, then we start talking about singular probability composition, correlation coefficient.
I'm not sure this is recording. Is it recording? I don't see it. But why? This will show me the.
They connect to each other. I don't know.
It said it was
It
recording.
will show the blue line of.
Hello. It's not. But they're on.
That's how we connected last time in the board.
So let's try one microphone and see whether here on that one. So try to speak here. Can you hear? What's her name? Savannah, can you hear us?
Yeah, you're good.
This is not working.
Hello.
Yeah, you're
Hello.
good.
Yeah. Yeah, we are good. Yeah. Good.
Hello.
Yeah.
Hello, Savannah.
This is not working.
But it's showing there that.
Yeah.
Okay, anyway.
Anyway, let's go. Okay, so and then we talked about what to take in the last class in detail and how it works, the mathematics and so on. So this is typically I used to give the assignment in my class. So go and see the visualization. And then I used to give a very big data of Twitter, and I used to ask, can you do acronym? Because Twitter is very well known for acronym. GNA is good night. Okay, MRNG is morning. So do acronym to fake and hashtag to fake and see how they're actually making meaningful things. But anyway, so let's move on. So any question, comment until this point? Yeah.
PPT.
PPT?
We want PPT.
We want the presentation. So this is crazy. I'll share the link. Very easy. Okay. Now, fine. We started talking about what vectors. What happened now?
It says
What happened? It's not connected. You should connect again.
Dr. Raj, if you just go back to your present.
Prezi got stopped. Okay, so what I'll start talking today is, okay, fine, we learn what to make and the basic things, but the question is how we can evaluate, because unless we evaluate and we get to some number, we as scientists, we don't believe anything until we empirically prove anything. So how you can prove that this is working and this is better than anything existing? So here's the point. So there are two ways to evaluate things. One is extrinsic, one is intrinsic. What is extrinsic? Very simple. You get a new vector, which is what to take, and you plug into some of your applications and see what the existing method is giving you versus what to do. Okay. Now another is intrinsic, which actually NLP community was very crazy about at the time. Versus what the vector space I'm creating is meaningful. So king-queen analogy, different kind of things started coming in. It's not that king-queen analogy born after Mikola write the paper. So this analogy data sets, there are many already existing from before 2013. more than 20 years. People have been trying to solve in different way. So now people will say, okay, now we have what to take. Can what to take solve this problem? Okay, so people started looking into it. Now, one obvious question is whether I do intrinsic evaluation, does it correlate with my extrinsic evaluation? Does it mean my good vector space is actually solving my problem? Or just we are actually, kind of, fulfilling our, our notion that, okay, if the vector space is good, then I'll be able to solve problem well. So is that notion right? So this 3 point we have to talk about. Okay, so what people started doing? So this is analogy. Okay, so what is analogy? So two problems. What similarity? What analogy? What is similarity? Man and human and user are same or synonymous word. And what is analogy? Man, woman versus king, queen. So how I can calculate? So this is the formula. Let's say XB and let's say X, A and B are similar word. And I'm trying to calculate whether they are similar to I and C. So man and queen versus king and queen. A man and woman versus king and queen. So I'll do what? I'll get the distance of X and B, A and B. I'll try to, plus XC and see the inverse of that with XI. And I'll do the similar with XB minus XA plus XC. So basically the distance between king and queen and the man and woman, how similar they are. That's my analogy task. I don't think it's very difficult to understand. Then people got crazy about what to pick, and they start saying or reporting in various papers, hey, it is working this way, it's working that way. So there are a lot of enthusiasm of that era around 15, 16. So for example, you can see that, the man, woman, and the, king, queen is, coming here. And if you see here, you can see the age distribution here, the gender here. This is more okay. So if you see x-axis wise, this is gender and this is age. So you can see princess, girl, and you see queen, aunt, wife, and you see nephew, princess, uncle, father, king, and so on. Okay, so one example. Now, real world are distributed in millions of ways. Age and gender is just one example. But people say this is happening. Then people started doing, again, age and gender, this is residual, and these are, related terms. If you search for Apple, iPhone, Macintosh, iPod, iMac, iTunes, and blah, blah, and this is the age, and this is gender distribution. This is 3-dimension, obviously. We can't do more than that visualization.
Yeah, apple could be fruit, right?
Sorry?
Yes, apple could be fruit.
Apple could be fruit. Absolutely. So what sense is a big question? I'll cover today. So again, similar globe visualization. So brother, niece, sister, uncle, man, woman, and so on. People say, this is from Manning paper actually. Say it is happening, the company and CEO is getting similar distances. Citigroup, Walmart, Viacom, Verizon, Vodafone, and so on. Then people say, not only that, we're also learning adjectives and their superlatives, slow, slower, shorter, and slowest. So we have a very unified relations. And so on. So people keep talking about this and try to solve this way. Then people. Yeah.
Question. If you're able to see so cleanly in 2 and 3 dimensions, the question coming to my mind is what is the other dimension?
Okay. Watson is a migration on this question. I'll cover today. Then I will be talking about this paper particularly because I want to emphasize on something. So you can go ahead and look at this paper, what this is, why this is. Yep. So here is the how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data sets. So this all data sets has synonymous word pairwise. Okay, so what people do, okay, you take all these words and try to see what is the distance in your vector space. What Tuvek is creating or globe is creating and so on. Okay, and this is the average Euclidean distance, 1.5. Okay, and these data sets are not created to evaluate what Tuvek. This is pre-existing. And there are, for example, there's a semi-eval. Yeah. So this task ran for almost 10 years before what Tuvek. Okay, so is a well-known task. So what Tuvek actually outperformed all existing methods of that time. People got crazy about it. Then other methods started coming in, the CBOW, and then n-gram to fake, dick to fake, SGNS, basically negative sampling, then globe come into picture, and all this data set, what is the kind of, these are F scores. So how this is actually performing. And similarly, so there are many other data sets. Okay, so this is important. I want to spend a little time here. So here you can see there are different data sets for the word relation, and the y-axis, I don't know why. Here, in the y-axis, you can see the task. Part of speech tagging, chunking, name entity recognition, sentiment analysis, two data set, IMDb and CNN, and the third one is sentiment analysis as well. Last one is machine translation and so on. Now the question is my intrinsic evaluation. So basically the vector space, making analogy, how it is correlated with the performance of my output into various NLP system. Part of speech, chunking, sentiment analysis, machine translation. You can see a higher correlation here, but it's not necessarily you are getting higher correlation in everywhere. So that's the point I mentioned in the extrinsic and intrinsic evaluation point, right? So if you read the paper, it says that, and this is the QVEC paper, the Chris Dyer paper I often get back to. So the answer is when you are seeing the numbers, they're from very different data set and their distributions are different. And what you were seeing in the machine translation might be different, but you see the high correlation here with this data set. It means that the words present into that data set is quite common with that one. Are you good are you good here? Yeah.
I'm not able to understand. So here we have the intrinsic evaluation task,
Right.
and across the x-axis we have
Y-axis. I mean, these are columns are extrinsic.
extrinsic.
Right.
What exactly is the correlation value? How are you getting that?
Okay, so if I am getting, let's say Euclidean distance and your performance, if they're close by, you are trying to correlate. If you are getting good value here, and if you are getting good performance there, so are they correlated? So it says yes, largely, if you have the same distribution in the data set for intrinsic evaluation versus extrinsic evaluation, your correlation would be higher. So basically the notion that I'm getting a more meaningful vector space to the real world analogy is true. Obviously, there are some, bits and pieces to left, but this is mostly true.
So overall, what insight can we draw from this entire business?
So basically what, the author also said that we need a kind of word overlap map with this, task or this data set versus this task. If you do that and then try to do this side by side, you can understand.
All this is solely in the terms of search, right?
No. These are NLP tasks, part of speech tagging, chunking, name entity recognition, sentiment analysis, machine task.
No, but while that, doing that would include search, right?
No,
In the application.
no, search has nothing to do here. So all NLP tasks, and these are word vectors. I mean, intrinsic evaluation. So the tasks are, to improve part of speech tagging, to improve chunking, to improve name entity recognition, to improve sentiment analysis, and machine translation. So these are tasks.
So if I have the correlation, we can include that.
Yes, you can, and you can,
Like,
correlate this way.
if the correlation is less, then what's the reason that people include that task for that specific?
No. So see, this era, what to fake is something. Okay, so let me. I don't know how to put it this way. See, Mikolov was not a big name. Okay, not his guide. I mean, his guide is not Edward Hobby. Okay, or something big guy in NLP. So when what to fake came into picture, people were skeptical. I have to evaluate how what to fake is working. Okay, and people evaluate in all possible ways. And it stands all such evaluation, and today is, is the method. So this is one evaluation method, which is telling intrinsic evaluation is good, but whether that has any translation to extrinsic evaluation.
checking out the correlation between intrinsic and extrinsic
Yes,
correlation. I mean, checking the
yes.
correlation.
So if I'm doing intrinsic good, does it mean it translates to extrinsic?
Okay,
Or the reverse? If I'm doing extrinsic good, does it mean intrinsic is good?
okay, if it is anti-correlated, like -1 values, then
Then it's not translating.
there is not.
Then it's not, translating.
So it's not effective.
It's not effective. Yes.
Anti-correlation.
Or negative correlation,
Yeah.
not anti-correlation. Negative correlation means it's not effective. So if I'm making good vector space, it is not solving my problem.
I'd be a little suspicious about that. If I had a big negative correlation, I'd be sure interested in what was going on there. It's diagnostic, it's just not
Yeah,
diagnostic
absolutely.
in the way that I want. I missed something, I was probably zoned out.
Mhm.
On the y-axis, these are different porphyra.
No, these are, come on. Come
I get-
on.
I get what's on the.
Yeah,
x-axis,
so
the
if you
y-axis.
see, these are data sets, right?
Those are the data sets, okay.
So these are the data set which
Okay.
has synonymous word pairwise.
Okay.
So I just talked about 10 here.
Uh-huh.
So if you look at that graph, it talks about around 30 or so. So these are all data set for intrinsic evaluation.
So those are data sets.
Yes,
On the.
and these are tasks.
The X is the
It
task,
has the
the
task,
and the
yes.
Y is data sets.
Yes, yes.
That's what I thought.
Yeah. Sorry.
What do these values say? Like, what does a high correlation mean?
Yeah, so this is right. -1 is the negative correlation, plus
Good job.
1 is a correlation, highest correlation.
Can we say that given that there is a very high correlation between the analogy task and the sentiment analysis, can we say that if we want to do sentiment analysis, then we use the analogy data sets? Is that
Yes and no. What I also said that. So the author did not do this. Okay. For example, you pick up machine translation data from WMP. And what if you pick up IMDb, sentiment analysis data? Now with this data, your word overlap is very less. So if you are not doing good on this task, but doing good on that task, that means that's good. On the reverse, if you don't have a word overlap, so that means does not correlate. So the question is, we have another table which says that from with this data set and that data set, how many number of words are actually overlapped.
So it will tell us to use that data set for the particular task or not.
Yes, absolutely.
So these data sets are available for all the tasks?
These data sets are independent of this task. These data sets are made to make word analogy. So they did not, this developed over 20 years. So they did not keep in mind for any task. Okay. And these are different tasks.
So is the point really you should use this data set for this task, or rather you should understand the relationship between the structure of the data set and the nature of your task?
Oh,
I mean,
so-
it's more of a scientific.
Agreed. So I'm just talking about that era, because people have been writing word embedding paper like, day and night. So if you look at any conference, there are 10 papers. And everybody is producing intrinsic result. In a vector space, my word vector is much closer in this data set. Now people come up with question, that is, you are self-obsessed. You are saying your intrinsic evaluation is good. Does it mean it will be actually helpful? Or the reverse? Okay, so that's the way people come up. Now, this is the era when what to fake was trained for a very small amount of data. Then people come up with 8 billion data set and so on, and it's trained on a huge data set. Then this question gone.
One last question about this table.
Mhm.
What's the basis of your big dividing lines here? Why are you assuming that these sets of, these data sets
These are
here
act-
have a certain similarity and et cetera?
Right.
And also the task demarcation.
Right. So these are actually from one, what to say, bucket. So this is a Google data set. This is a Microsoft data set. This is a semi-equal data set. And this is something else I forget.
Okay, and then the dividing line.
These are tasks, part of
Yeah, I
speech
know
tagging.
that, but big dividing
Okay,
lines
so
that
this is
mean something.
syntactic task, part of
Okay.
speech tagging, chunking, name and data recognition.
Mhm.
These are semantics, and machine translation is beyond,
All right.
the semantics.
So when it is anti-correlation or say negative correlation, So sometimes in clinical application, we just nullify that negative correlation. So here that happens also, like,
Yeah, absolutely.
but it is still able to predict that task.
Yeah, but I wouldn't just throw away something because there's a negative correlation. There's a clue there.
So, okay, let me, put this story this way. The goodness of what to say is an algorithm, okay? Now you can pre-train on a very large data set, or let's say you don't have it, you got a new data set, you can quickly run on your data set and create the work vectors, right? So if you have a correlation with existing, embedding, does not mean what today will not work for your data.
But it's negative correlation.
Yeah, that means not many word points are there which are correlated. That's why it's going negative, right?
But we nullify it sometimes.
What do you mean?
Negative correlation means they are just opposite of each other. Right?
Yeah.
One is
Yes, that's true. And also it is true that when you are getting many points which is not correlated, so overall the number is going down.
If you multiply it -1, that negative correlation will just convert it into positive
Right.
correlation. And then it will be a like positive correlation.
It's still meaningful. It's still your point.
It's still meaningful.
Yeah, another
Yeah.
criticism about this. These are R's. So, when you do R squared, which is percent variance accounted for, pretty clear to me that you've got plenty of room for improvement,
Yes, absolutely.
right? I mean, our best shot is probably around 50% variance accounted for, something like
Agreed.
that.
Agreed.
Why is as far as I understand, these data sets have no relation with the task.
Right. So that's the point I was trying to say here.
Why do you think like certain data sets perform
Right.
better than certain?
Okay, so that's the point I made, that sometimes what is happening, that this data set versus that data set don't have much word overlap. So that's a problem. Given the time this paper has been written. Even that time, what to take trained on 8 billion data set is still not released. Okay, now that overlap question is nullified today because it has been trained on a huge data set. So out of vocabulary is beyond question now.
So is that the point, or you could also make the point that you've been making before, which is that we really need to think hard about the design of our benchmark corpora and data sets.
Absolutely, that's true.
And its properties.
Yeah, absolutely. But this is the time when people have been evaluating this prediction-based mechanism of word vector and how they evaluate it. You can relook and you can discover many things else. But are we good here? Let's make sure that we are firm here. Then I'll go. Okay. So now, so I believe now the controversy begins. Okay. So it happens although it's in science. Okay. So when a new theory comes and which actually says, hey, what you did in last 40 years, all nonsense. Now it's a new model coming. Okay. And obviously people, become, kind of, skeptical or insecure. The first man who actually adopted this is man. And hats off to that guy. He spent his lifetime in dependency parsing, but he's still open to new ideas. He just released the paper in two years long. But there are a lot of people who object to this idea and started fighting back and so on. So there was a lot of discussion and debate in the NLP community. So then what we did in the last 40 years all nonsense. Okay, and now this paper comes in picture. We said no, it's not like that. There's a bridge between these two. So Omer Leahy come into picture. He was a postdoc in Washington at that time, and he wrote this paper. And it got so much attention of that time, which made the right bridge between the distributional semantics of SVD era to the prediction-based one. Megha, would you like to talk about this? Yeah. So I would like to spend some time here. Actually, not me, Megha. So over to you, Megha. This is the basis of our imaginator paper. We stand on this. Okay.
All right, so from the premise that Dr. Das already gave, this paper talks about a bridge between the traditional count-based way in which word embeddings were made along versus, let's say, the neural embeddings. So in this paper, they have performed very systematically
just for everybody's understanding, just read out clearly the abstract.
Yeah. This is a very well written
No, read out,
abstract
read
in,
out
in
loud.
fact, yeah. So recent trends suggest that neural network inspired word embedding models outperform traditional count-based distributional models on word similarity and analogy detection tasks. We reveal that much of the performance gains of word embeddings are due to certain system design choices and hyperparameter optimizations rather than the embedding algorithms themselves. Furthermore, we show that these modifications can be transferred to traditional distributional models, yielding similar gains. In contrast to prior reports, we observe mostly local or insignificant performance differences between the methods, with no global advantage to any single approach over the others.
What
Now-
is this paper?
Yes. Now, this is a very bold claim to make in the year 2015-16, when everybody was so hyped up about word2vec and glove. And these two guys came and said that, oh, mathematically, the objective that they are trying to solve is just very slightly functionally different from the traditional count-based models. And how they have performed their experience.
This abstract was intended for that to be a bad thing.
No, it was not at all intended to be a bad thing.
So
It
they
was,
said we did not see any method winning.
yes.
One hyperparameter could be transferred here,
Right.
or one setting could be transferred there. So we don't see any global benefit of using this versus that.
So basically, they proved via a very well-controlled set of experiments that it was the hyperparameter tuning or the way you control the variables of your embedding models rather than the algorithm that made the model itself. Sorry, rather than the algorithmic model that made the embedding itself.
Cops do this all the time, and it makes people in other scientific disciplines crazy. You have way too many free parameters that are contributing to the success of your models,
Yes.
which is why I always ask you guys, where's your ablation study?
This is an excellent, it's a very well-written, structurally organized paper.
And this is what,
And-
where you can the paper today.
For it, swap them, change them, vary them, look at the sensitivity of your results with respect to the arbitrary or unjustified choices that you made in the design of your system. It could very well be those incidental features that are responsible for your success. It has nothing to do at all with what you are claiming it's due to. You're gonna have to figure out a heuristic for searching the space. But I don't see how we have a science unless we can understand, unless we can do credit assignment, understand how the outcome is related to a specific feature in our system. So there is no like emergence. It might get, it sort of tells you you're in the right place, but you guys have like, 50, 100 different things that you think around with to make your system successful. And then when you do machine learning classification, you do like 6 different methods for that. Most scientists look at that and go, this is nuts.
So Dr. Shalin, this paper will probably make you very happy in
It
terms of
Exactly.
answering your questions. So the same author.
Just a comment. We will go. So I was present during this paper presentation, okay? And in that time, there used to be, actually 2 school of people, okay? So so all people used to sit in one side, I don't believe this vector thing. And the new people who believe in vector thing, they used to sit in the other direction. So when this paper presentation is over, so it seems that both the school are happy, So we both win kind of thing, and situation happen and so on. Anyway.
Yeah. So the same authors have a series of work. It's an entire body of work. And this paper specifically, it mathematically shows that the word2vec's SGNS model is implicitly factorizing a word context PMI matrix. Now, I have chosen not to go into the details because sir already told us about the word2vec's final model was the SGNS1. And we already know what the word context PMI matrix is. So basically they had showed that. So do you have that paper open, or maybe it will come up later? So
Yeah, I
basically,
have the paper. You want to show that paper?
I
The
just,
second one,
just
right?
a quick, just a quick
This one?
look of the, yeah. Yes, so this is that paper that they were talking about, and they have shown shown that it is the factorization, and towards the end. So basically this is it. This formula right here. So we know that this MPMI is the word context PMI matrix minus log K, where K is your context window size. This is exactly what word to vec is. Nothing new, nothing more special or anything. And I think at that time, this must have been a phenomenal thing to mathematically prove. So having shown that it's quite similar to the neural embedding model, what then is the source of superiority in neural embeddings, if any? So
Can I just ask one quick question? So I don't follow all of the language here, but is the notion that there are different algorithms for implementing the same functionality? Is that
yes.
a way of
Yes.
summarizing what's going on here?
Yes,
Okay.
exactly. So basically they have experimented with 4 different models, 2 of them being neural embedding based, neural network based, and 2 of them being traditional count based approaches. And by carefully choosing for each algorithm, by carefully choosing which hyperparameters or which variables to control, they have performed experiments that I will show very shortly. And after all these experimentations, they have concluded that the hyperparameters are what have the most substantial impact on the performance of each model. So as I just mentioned, hyperparameter tuning significantly improves performance in every task. So let's just quickly go through some notations that will help us understand. Do you mind if I is this still readable for everyone?
Not really.
No? Okay.
But
And I'm not gonna read it.
but you will be speaking up, right?
Okay, no worries, no worries. Let's just focus over here. So there is a word vocabulary, VW, in which each word is W. There is a context vocabulary, VC, in which each potential context is represented as C. And we have something called D, which basically gives me a count of how many occurrences of W and C occur together. So for example, if you want to find the embedding of the word W, and as we know, the word to vec looks at its context. So your C is the context that comes along with W, and D is just a matrix that will have VW matrix cross VC matrix, number of cells in which each cell represents the number of times the pair WC appears in your.
Okay, so just to
Okay.
add what Megha said, remember, we talked about co-location matrix, right? So basically, this every word occur with every other word how many times. Then we say we are using raw count. That's not good. Okay, let us do, kind of factor it with the vocabulary size. Then we say, no, let's do PMI. Let's do PPMI. Let's do log PMI. Let's do this and that. Okay, so we did a lot of things. Then do smoothing. Then do, correlation coefficient and so on. So people have been creating this vector for what, right? This is the way. So now these guys are drawing analogy based on that count-based method and what I'm doing now prediction-based method, how this is correlated.
How did they did the hyperparameter
Yeah,
Here.
exactly.
It's this is just the notation. So this notation is followed throughout the paper. So make sure you understand what everything means. So the most traditional representation, which was the positive pointwise mutual information matrix, PPMI, is given, the PMI is given like so, which we already discussed in class. And this is the actual numbers that come here in the log ratio. And when you want to do positive PMI, you just replace any non-negative values by 0. So that's here. And that is your traditional explicit PPMI representation. Then we also looked at SVD, which is the singular value decomposition, in which our entire matrix of word is basically factorized into U sigma VT, where if you recall, W and C were supposed to be the word and context matrices, which is now broken down as W equals UD into sigma D, and V is the VT. Sorry, C is the VT. Yeah, here they distributed. So once again, in PMI here in your matrix, each cell gives you the PMI count, and each row of the M matrix is basically the vector which you get after calculating the PPMI of each word and its context. For singular value decomposition, this is how you break up the matrix. Now, these two that I just spoke of, the PPMI and the SVD, these two are the traditional count-based approaches of getting a word embedding. The next two are the neural embeddings. So this is SGNS, which is skipgrams with negative sampling.
Although I did not teach negative sampling here, I'll talk about that. And we have 5 minutes now.
Oh, okay. This is stressful. So SGNS as implicit matrix factorization, which I just showed in the previous paper, exactly says this. Okay, so basically they proved it mathematically. Go ahead and read it if you want. It's a nice paper. It shows that in SGNS, the way the matrix is factorized is just your original PMI matrix minus a global constant log K, where K is the size of your context window. And finally, we look at GLOVE as our fourth algorithm, which is also a neural network-based algorithm, in which our vectors look something of this sort. This is something that the machine is trained to learn and optimize, and that is how you get the embeddings for the GLOVE. This was done just so as to, you make the notations uniform across the entire paper. Now let's quickly go on to the transferable parameters. Now, this section talks about what are the various hyperparameters that were involved in training your word2vec or GLOVE, and how we can apply or how we can adapt these hyperparameters into our traditional count-based models and improve their performances therefore. So they have divided hyperparameters into 3 different parts. One is the pre-processing, then the association, and finally post-processing. In pre-processing, they talk about something called a dynamic context window. This was mostly popularized in the word2vec and GLOVE, where both of these models used a different way in which they weighted the contexts for the target word. So for example, the intuition that was followed through in both the models is that contexts that are closer to the target are more important. This is something we all unanimously agree most of the times. So in word2vec, the way they had weighted was by weighing by the distance from the focus word divided by the window size. So for example, a size of 5 window will have these weights for each of the context words. For GLOVE, it was a harmonic weighting. And for this purpose, they have used the word2vec style of sampling the dynamic context window. So basically what this says is dynamic context window is one of your hyperparameters, which basically tells you how much weight you are supposed to give to each of your context words. And here they have followed this particular kind that word2vec does. All right, then we have subsampling, which is basically similar to removing stop words in your pre-processing algorithm. And this is the formulation where you define some threshold T, and they have used T equals T in 10 to the power minus 5 divided by the frequency of the word. And this is your probability of which, by which you decide how many words or which words to subsample. So the implication is that removal, sorry, not implication, a detail of the subsampling is that the removal of these tokens, the subsampling is done before the corpus is processed for the into the word context pair. And we call this dirty subsampling technique as opposed to clean subsampling, which, as mentioned here, sorry, remove subsampled words without affecting the context size. I don't have time to go into details now.
The start of the paper, the question which was asked was, why this embedding was like performing better than the normal count based, like
Yes,
which is both.
yes.
This is the answer to that, like these,
All of these.
like this transferable parameter.
Yes, yes, exactly, exactly. So when word to wear and glove came into picture, people got very excited about, oh my God, what is this, something great that we have invented. But then these guys came and said that, oh, you're not doing something very extraordinary from the traditional count-based methods. Basically, why your model is performing so well is because the hyperparameters have been tuned in such a way that it's performing better. If you use these same hyperparameters on your traditional count-based methods, we will see in the experimentation that the traditional count-based methods have actually outperformed the neural embedding methods. So these three were the pre-processing hyperparameters. Then we have the second type of hyperparameters, which are the association metric hyperparameters, which are, this is called a shifted PMI, which is nothing fancy again. It's just the positive PMI shifted by the same log K global constant that we found before.
Hyperparameters which we have mentioned.
Yes. They have. They do.
Yeah.
Wait for it. So this is one. Then we have the context distribution smoothing. Basically, what this does is it changes the way you calculate your PMI. That is basically just giving an exponent to the exact count of the number, and that is how they are smoothing the numbers. And here they have experimented with two different exponents. Alpha equals 1 refers to the unsmoothened PMI, which is your original PMI, and 0.75 as the smooth PMI. Finally, we have some post-processing hyperparameters in which one of the techniques is adding the context vectors, and this idea was introduced first in the glove paper, which none of the other people thought of. And basically here what they did was you get the W embedding from the original W matrix, but along with that, you also add the context vector to get the final embedding. This was one of the novelties in the glove paper and why it was popular. Yes, you can think of it that way.
Okay, so just to add to that. So after this, so glove is a mixture of count-based method and prediction-based method. So which I will talk later on. Today we don't have time, but we'll come there.
Yeah.
Sure.
Okay. And the final hyperparameter or final or penultimate, I don't remember, is the eigenvalue weighting. So if you recall in SVD, we saw that there was your W was UD into sigma D and C was VD. How about if you didn't do it exactly like that, but put some sort of a symmetric multiplication over there. So this is basically weighting the eigenvalue matrix to distribute it across the word and the context matrices. So the way they have the parameters that they have tuned here are, so consider P to be the exponent of how much you're multiplying. Here they have experimented with P is equal to 0, which essentially means that there is absolutely, you're nullifying the eigenvalue matrix altogether. P is equal to 0.5, which corresponds to this equation right here. And P is equal to 1, which is your traditional SVD. Finally, we are doing vector normalization, which is L2 normalization divided by the length of the vector, and you get a unit length vector. All right. So these being your hyperparameters, this table showing the hyperparameters. Now, we need to understand that due to the structure of the models, not all of these hyperparameter tuning are applicable to all of these 4 models. So this table shows each hyperparameter, what are the values that they have tuned, and for which of the 4 methods this is applicable to. Having said this, we move on to the experimental setup. And they have, I mean, I tried to do the math and it matches, like these number match these things over here. And these are all their hyperparameter space experimentation. So the word representation for the corpus, they have used a similar corpus that Sir was just discussing about. If you will recognize some of the names that we just saw. So for word similarity, they have measured between similarity and relatedness. Sir, maybe later if you could explain the difference between similarity and relatedness, I did not get that. And for analogy, they have used the Google analogy task and, Google analogy data set and Microsoft analogy data set. And the way they have evaluated the analogy is 2 different metrics, 3 cos add and 3 cos mul. And this is the formulation. Now, results. So table 2 shows the vanilla scenario where all hyperparameters are set to default and everything is the same. And you can see that in some tasks, in most of the tasks, SVD outperforms the other methods. Only in the Mechanical Turk data set, we see that word2vec has outperformed the other tasks. Glove hardly ever outperforms any other task. And in analogy, we see that only PPMI does even comparably better than any other task. So you can go through all of these tables in detail, but due to our time constraint, let's just quickly go through the results. So basically, they have concluded that careful hyperparameter tuning can outweigh the importance of, they had added more data and tried to do that. And it all boiled down to having a good control over your variables. Yeah. So an interesting observation is that there is no single method that consistently performs better than the rest. Training word vectors from large corpora is mostly computationally costly. You could use that time and compute into tuning your hyperparameters better. And overall, there does not seem to be a consistent, this is like a repetitive idea that keeps coming up in this paper, that even though it seemed like a remarkable breakthrough of creating word embeddings through neural networks, it performed just as well, if not better, than your traditional count-based methods. So I think that is the gist of it.
So after all this said and done, why has the neural network-based method then persisted?
Well, one thing we want to note here is that this is from a time before the transformers came. Nowadays, well, word2vec is popular, glove is popular, but we in our Imaginator paper have gone back to our traditional count-based methods to create our joint embeddings. I couldn't say why the neural network models have persisted. Maybe sir could help out over there.
You were answering this. So you answer.
Yeah.
Is there any, I don't think so, but there's no efficiency advantage for people. I'd be surprised.
I don't see it being more computationally effective, because even in order to create a neural network embedding, you will have to do a lot of training, which is also computationally effective. Here you are doing matrix multiplication, which is also kind of computationally effective. So that kind of balances.
Did you have a link to this, or is this paper posted?
Yeah, so, yeah, I can post it.
Yeah, so, you know, this is a psychologist, looks like science to me. And stuff.
Yes. So, yeah. Moving forward, they have just given some recommendations about tuning parameters.
Question, comment? No question? Yeah, that question. So the answer to that is for vector space. So when we do in a count-based method at the bottom up, so that vector space is even very difficult. And when we go to, the WSD problem, we want to solve in the vector space, a neural setup. We want to solve many other compositional problems. So let's say I don't like chocolate and I like chocolate, syntactic dependency. So the vector space is very different when you do the basic count-based method and singular variety composition. And word2vec actually solve that problem in a very large scale, because you can train it on very any given data points, and that quickly creates that. So those two are the reason people moved on towards word2vec.
Isn't it something to do with the type of problem you are trying to solve?
No, so I believe this method outperform all the
No, because it is mostly lower level of abstraction syntactic test evaluations.
So it performed well in all the syntactic tasks, let's say part of speech chunking and kind of thing. It did well on all the semantic style, let's say analysis, kind of entailment kind of problem. It also did well on complex tasks like machine translation and so on.
What about something like intent detection?
Yeah, it's intent detection is very easy. So if you see the yeah, it is okay. So
Okay, well.
yeah. So see syntax detection. Let me go here. Yeah, whoever wants to go, they can go. We can.
So, but I had a question. The WSD problem and having a good vector space that you said, wouldn't that have reflected in the word similarity or word analogy tasks?
Yeah, I'm coming to that. Okay, let me. So okay, so this is the father of intent detection. Okay, so 1980s work of switchboard corpus from Stanford University. So basically, Juravsky's first work being a system professor. So on this data, I believe with the neural model has gone to around 93%. So,
What's the space of intents? So
Yeah.
I'll tell you one of our intents.
yeah.
We wrote something in about 5 years ago.
Yeah, these are
detecting
43.
different Suppliers in an emergency response situation.
Okay.
That's the kind of intent. I
No,
want
this
to
is
find.
a this is a different kind.
Yeah, this
It's a
is
different kind of
just
intent.
open-ended dialogue. And this is the classical work actually, from where the intent, the term intent detection, etc., actually born. So this is that work which started this.
Okay.
Yeah, intent to help and receive help is a
Yeah, that's
specific kind of.
specific
Well,
kind of.
that's an example of a higher level task
Hmm.
that requires domain knowledge, in my opinion, and the kind of thing that, we've been working on. Nice, very nice.
Okay, let's stop the recording and
When did you have a question? Oh.
Ranjit, can you where are the two this thing?
Yeah.